Welcome to T1 Day 9 of Honors Precalculus. This is part 2 of our review for the test. So we're going to find, in this one, we're going to look for all of the discontinuities of the function below and state the type of each and the end behaviors. So the first thing we do when we have a rational function is a polynomial over a polynomial, is to factor. This numerator factors into x minus 3 times x plus 2. And then you can factor the bottom one by grouping, by first looking at these two and then looking at these two. You factor out an x squared from the first two and you end up with x plus 5. And then you factor out a negative 9 from the second two and you end up with x plus 5. So there you have the x plus 5s in both cases. So the fully factored form is x minus 3, x plus 2 over x squared minus 9, x plus 5. And now you'll notice that this new section here, that's a difference of squares, so it is factorable. Keep going. Really important. So you end up with x minus 3, same numerator, over the difference of squares, x plus 3, x minus 3, x plus 5. Now, we can cancel something here, the x minus 3, so that tells us there's a whole when the x makes this 0, so that would be whole when x is equal to 3. So the fully simplified version of this is x plus 2 over x plus 3, x plus 5. And if we wanted to know where the whole actually is, you would have to plug 3 into this function right there. So that would be 3 plus 2 over 3 plus 3, 3 plus 5, 5 over 6 times 8. So it's 5 over 48. So where's the whole? The whole is at 3 comma 5 over 48. Now what about other discontinuities? Well, now you can't take away this x plus 3, so that means there's going to be a vertical asymptote at x equals negative 3. And then right here at x plus 5, it means that there's going to be a vertical asymptote at x equals negative 5. Those are the two things that make the denominator equal to 0. But let's take a look now for the end behavior. What happens to this as x gets infinitely big? Well, you look at the original here, and you'll notice that the degree here, the degree of the top is 2, and the degree of the bottom is 3. Because the degree is greater on the bottom, you know that the end behaviors are going to both go to 0. So what this means is as x goes to infinity, g of x goes to 0, because the bottom is going to get infinitely bigger than the top. And this could be positive or negative, but anything that has a huge denominator, positive or negative, is just going to 0 from either side. It's okay not to put the plus or minus for sidedness, but you have to put in, though, that the limit in both of these goes to, not 8, it's infinity. I gotta write that sideways right there. There it is. How do you verify that two functions are inverses of one another? You have to do f of g of x and show that that equals x. And you have to do g of f of x and show that that equals x. You have to plug both functions into each other in both orders. So what is f of g of x? You take g of x and you plug it in. So f of g of x, you take g of x and you plug it in. So it's going to be, here's f, 3 times g of x minus 1 to the third plus 4. So instead of g of x, what are we going to write? Here's our g of x right there. We're going to take that and plug it in right there. So that equals, get the pen right there, equals 3 times the cube root of x minus 4 over 3 plus 1. That is g of x right there. We plugged it in 4x, and there's this minus 1 still here, and it's cubed plus 4. Well, the nice thing that happens here is this cancels, and then you end up with 3 times the cube root of x minus 4 over 3 cubed. When you cube something that's cube rooted, they go away. It's like squaring a square root. So this is just going to be 3 times x minus 4 over 3 plus 4. What cancels here? The 3's cancel. So you end up with x minus 4 plus 4 is equal to x. So that's the first direction. The second direction, you have to go the opposite direction as well. We're going to take f and plug it into, g. So here's f right here, and we're going to plug it into x. So what that means is you're going to have g of f of x. That means you're plugging in f of x in. So it's going to be cube root of minus 4 over 3 plus 1. And what we're plugging in there is f of x. So it looks big and nasty, but it's going to simplify. 3x minus 1 cubed plus 4. Well, look what happens. The plus 4 and the minus 4 cancels, and then the 3 cancels, so you're left with the cube root of x minus 1 cubed plus 1. Well, the cube root of something cubed, it goes away. It's like taking the square root of something squared. It's just x minus 1 plus 1 is x. So we've shown both things. So to show something is an inverse of each other, to prove it, you have to show this and this. Plug one function into the other and vice versa. Is that function right here, is this invertible? Well, it is if it's one-to-one. But you can check this easily because does it pass the horizontal line test? Well, you know that it has how many x-intercepts on this? It has how many x-intercepts? Well, at 4, 0, because of this term, and because at 5, 0, and at negative 2, 0. It means that this function does a bunch of things, but it hits the x-axis in 3 places. So one way to see if it's invertible is if it passes the horizontal line test. Well, is there a horizontal line that passes through more than one point? Yes, there is. So therefore it is not. It is not one-to-one, not 1 to 1. So it's not invertible. You just find if there's a horizontal line that passes through more than one point, and there is, the 3 zeros. Finding two functions that compose together to get a third leaves you usually with more than one possibility. So what you're looking for is a function f, so that when you plug in g for x, you end up with this whole thing. So one way to think about that is h of x is going to be f of g of x, meaning you're plugging in g into f. So one way to start is just pick something that's a piece of this, like a shell. I'm going to say f of x is equal to negative the cube root of x minus 5. And I'm going to say g of x is equal to 2x plus 4. What does that mean? It means when you do f of g of x, you take g right here, you take g and you plug it into x. And then you would end up with that. So you literally can pick, there's a couple other ways, but that's the most straightforward. I really like that one. There's other ways, but that's the most straightforward. You take g, you replace it for x here, and you end up with what you want. So now we're going to graph a piecewise function, negative 2x minus 12. Well, that crosses at negative 6. It crosses at negative 6 and has a slope of negative 2. And we know that's going to have an open dot when it crosses at x equals negative 3. So it goes down a little bit to here, and then it goes down to here, and there's an open dot. So this function right here starts at that open dot, and it's a straight line like that. Open dot. Let's just do the other side. I kind of want to skip over to the other side. X minus 5 when x is greater than or equal to 1. So that starts, it would cross here if it went to 0, but it doesn't. It starts at 1. It's got a slope of 1, so it's actually going to be a closed dot right here. It's going to have a slope of 1. So this thing just goes up at a slope of 1. So this blue one goes up like this. Okay, that's great. So what about x plus 2 squared minus 7? What you want to do there is look at what happens when x is negative 3. So negative 3 plus 2 squared minus 7. So that's negative 1 squared minus 7. So that's 1 minus 7 is negative 6. So we know the point negative 3, negative 6 is there. Negative 3, negative 6. Oh, we got to extend this. I didn't extend this all the way. This needs to go all the way to negative 3. So that's there. It goes all the way to here. So that green goes all the way to here. And then this one takes over. This middle one, we'll make it yellow, does start right here. So it does start right there, so it would fill in. But then it's a parabola. It stretches down and then goes up. So where is the other endpoint? Well, if you plug in 1 into this, you get 1 plus 2 squared minus 7. 3 squared minus 7 is 9 minus 7 is 2. So you know that this point is an open dot at 1, 2, like this. That point right there is 1, 2. You could do the y-intercept when x is equal to 0. X equals 0 is the y-intercept for this one we want to do. So you could do 0 plus 2 squared minus 7 is 4 minus 7 is negative 3. So it's actually right there. So it's going to be a parabola like this. So that's what it would look like. So you need to answer the rest of the question. What are the discontinuities? Well, where do you have to pick up your pen if you were drawing this? Well, it joins right there, but you do have to pick it up here. There is a jump discontinuity right there. There's a jump discontinuity at x equals 1.